While you guys were on break, I went to Multisim and I created two little circuits. Um, one of them is a DC circuit, and one of them is an AC circuit. And then basically turned on the oscilloscope function. And the green line here is AC or DC?
DC.
DC. And this is?
AC.
So it's really, I mean, it's a real snapshot in time. You have the time down here. I just happened to stop it at a specific time. It didn't zero itself out. But you can see that AC, here's 0, so it's up, then it swings negative, positive and negative. And the DC equivalent would be, this peaks out at?
9.949.
Well, 10, actually. I set it for 10. So at 10, and DC equivalent would be? 707. So there we go. Well, since I'm here and this is on, we should probably take just a minute and I could show you briefly how this works. If you want to use it, I mean, you're absolutely welcome to do it. I'm sure there's a quicker way to clear everything. Probably just, I don't know, I haven't messed with it too much, so.
What is this called?
Untitled circuit.
Untitled circuit?
No, it's right there. It says multisim.com. It's free. All right, so if I wanted to create a circuit, I'm going to come over here to this right here. Here's my power supplies. Click on it and pick what I want. Do you want AC voltage? That allows me to set the voltage. This allows me to set the current. There's different types of waveforms that we're not going to get into that you can set, but there's just DC voltage. Click it, click here. Now I've got a voltage, and then I come over here and pick a load. So I just pick a simple resistor, bring it over here. I want to rotate it. All right, then to connect, just hover right over there. A little spool, like it's a spool of wire. Just click on it there, over here. There, done. Done. There's the circuit. Turn it on, boom, it's running. Stop it, and then if you want to, when you stop it, you get some more tools. If you want to measure stuff, we'll measure voltage. So we can measure the voltage drop across here. Drop it there, it drops a voltage pin. Then you have to hit the negative right there and drop it where you want the negative. And if I want to measure the current, back to here, pick up current, place it where I want to measure current. Don't need two probes because it's in series. And then go ahead and run it. We'll see that we have 5 milliamps at 5 volts. If I want to change anything, just like if I want to change the battery, you can slide it right there, or you come over here and you can change it here. So 15 volts. There you go. Rerun it. You get that.
Can you draw schematics on this program?
I just did, right?
I mean, can you like draw full on like schematics for everything like that, or is it all just?
No, I don't. You could draw a schematic like that. That's what I was saying. I think you could, I clean this up a little bit. Oops, stop it.
Is this what you would say like is a good program to draw a schematic on?
I don't know about that. It's just something I've just kind of discovered. There is a project where you are going to use logic gates. I have not used this one yet. I don't know if this does logic. There's logic gates right there. So digital and or NAND NOR XOR. Yeah. So we have logic gates we can put into this thing. Make 3 logic gate circuits, make it run, because it's one of the projects you'll do is to use something like this and do a logic gate circuit. So you could do that. Anyway, back to our regularly scheduled program. And we were talking about all meters need current flow to register. And then one of the things I said, and I'll now write it, Sarah, so voltage meters, actually read current flow calibrated to show volts based on This is going to blow your mind. Ohm's law. Which is E equals I over R.
So, if when you're putting a voltmeter in parallel with a series circuit, why wouldn't it just blow up like a ammeter would if you put it in parallel with a series circuit?
Hang on one second. Proportional to voltage. Say what now?
So, if a voltmeter is actually reading current like an ammeter would,
A voltmeter is actually reading current like an ammeter.
then why wouldn't it blow up if you put it in parallel with a series circuit like an ammeter would? Or not blow up, but it would blow the fuse.
Because internally to the voltage, to the meter itself, when you are measuring current flow for real, it has very, very low resistance. And it shunts a tiny, tiny amount of current up through the meter, back down, and around. So within it, you're creating a little parallel circuit that steals off a little bit of current. But there's very, very little resistance to that. So when you hook it up across something, you're getting that problem. And with a voltage meter, you have very, very high resistance. So when you put it in series, the high resistance internally blocks most of the current from coming in to keep from damaging it.
Got it.
All right. This is good to know because I think about it all the time when you're using your meters. Why is the meter only about yay big? How come it doesn't go around in circles? I mean, wouldn't that be nicer? So most meters have about 100 degrees of usable range. Due to principles of magnetism. Due to principles of magnetism. In other words, your magnetism, it's too difficult to do it because you have inverse laws with magnetism about how close things are and how far away they are and how it affects something. So you have to keep it within that. I even wrote that. Magnetic force acting on a substance is inversely proportional to distance, which is to say the further the distance, the less the force. So meters can only read a certain range before the magnetism is actually out of range and no longer works. And for some unknown reason, this is the point where I decided to add this. Let me see. The Wheatstone bridge circuit. These things are everywhere. I'm going to try and spell it so you can actually follow. Wheatstone bridge circuit. Also called a resistance bridge. It looks like this. Look somewhat familiar?
Yeah. Looks like shredded wheat.
It looks like the, a little bit like the rectifier bridge circuit. Let me see, did I put a... I did not. All right. Back to this. All right, Wheatstone bridge circuit. A diamond-shaped circuit whose concept was developed by...
Mr. Wheatstone.
Come on, man. Mr. Bridge. Yes. By Charles Wheatstone, can be used to accurately measure unknown resistance values or as a means of calibrating measuring instruments, voltmeters, ammeters, by the use of variable resistance and a simple mathematic formula. So we shall write that in a condensed version. We will say a diamond-shaped circuit used to, I'm going to say a means, this will make more sense, means to calibrate measuring instruments voltmeters, ammeters, ohmmeters, etc. By the use of a variable resistance.
So why wouldn't you just be able to use like a potentiometer in this case?
You are, actually. One of these is. So, like that one. All right. I'm going to stick with my notes because there's I don't think I've had this before. This is like a new thing I'm introducing. I don't think I taught this last year. So I'll stick with my notes just to make sure I do it correctly. So the Wheatstone Bridge. How are you doing that? Oh, it's touching that. The Wheatstone Bridge, I'll just abbreviate WB. The WB, Wheatstone Bridge, is nothing more than two simple series parallel arrangement of resistances connected between a voltage supply. Between a voltage supply terminal and ground producing zero voltage. Let me say between a voltage supply terminal and ground producing zero voltage. And ground, comma, that'll make more sense. Producing zero voltage difference between the two parallel branches when balanced. Difference between branches when balanced. And I will tell you what that means. I'm going to go back up a little bit. So, the Wheatstone Bridge circuit is nothing more than two simple series parallel. Can you see the series parallel? Series parallel. These two are in? Series. And those two are in? All right. Nothing more than two simple series parallel arrangements of resistances connected between a voltage supply. Connected between a voltage supply. There we go, because I didn't write that in. Between a voltage supply, terminal, and ground. Voltage supply, terminal, and ground. I don't like the way they wrote it. Producing zero voltage difference right here. Producing zero voltage difference between the two circuits when balanced. So if these two resistors equal these two resistors, then there will be no difference of potential between, we'll say, points A and B. And I hope that you can see that.
They all have to be the same, or does it just have to equal the same?
This branch and this branch No, they have to be this. They have to equal.
Well,
If
what do you
anything
mean?
is out of balance,
So it doesn't matter the value of each resistor, they just have to be equal to show.
correct.
So you could have a 50 ohm resistor and a 100 ohm resistor, and then you could have a 75 ohm resistor and a 75 ohm resistor.
Think about that. If we had 50 ohms and
And
20 ohms, right? And then, well, it'd have to be 50 ohms and 20 ohms. There would be the voltage drop between this and this and this and this would not be the same. Therefore, this spot and this spot would be different, correct? And if this spot here, we'll call that C and D. If C and D are different, then voltage is going to flow through C and D.
So they'll have to be the same.
So they have to be the same. Which is why you're going to see in a minute we have one of these is be able to balance out to make sure that it balances.
Hey, Kevin?
Yes.
The same as in like all four resistors have to be 50, 50, 50.
Well, let's take a look and see where I'm going with my notes. Just because I'm going to show you some examples and we'll see exactly what happens. And I think you'll get it. I don't think I need to write this. Wheatstone bridge circuit has 2 input terminals and 2 output terminals. Yeah, let's stick with it. Has 2 input and 2 output terminals. And again, these Wheatstone bridge, they're in, it seems like everything. You look at a schematic for anything, you're like, why is there a Wheatstone bridge right in the middle of that thing? So, and I know that this is going to come up time, even through second year, when you get into, and I think this is one of the reasons I thought I really got to cover this, is because when you get into fire detection systems, I believe Phil does a lot with the Wheatstone bridge on there and expects you to know it. 2 output terminals consisting of 4 resistors configured in a diamond shape. Okay, we don't need it. We already said that. When balanced, the Wheatstone bridge can be analyzed simply as 2 strings in parallel, which we did that. All right, so here's one here. So I have an example here. Let me see. So if this is 10 ohms, and this is 20 ohms, and this is 12 volts, what is my voltage drop across each one? So if you haven't been paying attention, that'd be EIR for each.
1.2 on the first one.
And so we have 30 ohms. I don't know if I guess I did. So what is my current flow? And that's, you know,
0.4 amps.
E equals I over R, in case you forgot. So 12 divided by 30 is 0.4.
Yep.
0.4 amps. All right, so this is 0.4 amps, and this is 0.4 amps. What's my voltage drop across each one?
4 volts and 8 volts.
4 volts and 8 volts. All right, so let's see. One side of the string has a 10 ohm and a 20 ohm resistor. The voltage drop is 4 and 8. If the other side of the bridge is the same, the other side is the same, and I have point C and point D, C and D, and this is a 10 ohm and this is a 20 ohm. What is my voltage drop right here?
4 volts.
4 volts, and what's my voltage drop here?
8 volts.
All right, so if I have 4 volts there drop and an 8 volt there, what is the difference in potential between C and D?
0 volts.
So that'd be 0 volts right there?
Yeah.
Okay, you are correct. So that Wheatstone bridge is called
Balanced.
balanced. Okay. Now, let's try this out over here. Let's, if we can remember those numbers, we will do 10 ohms, 20 ohms, let me see. What do I want to do? It says now reverse 3 and 4. reverse, hang on, reverse 3 and 4. Oh, reverse 3 and 4. I think I cut off some of my drawing, which is the problem. Anyway, now reverse 3 and 4. Let's do that. So 20 ohms and 10 ohms. So this was 4 volts, and this was 8 volts. That makes this 8 volts. That makes this 4 volts. So what are we going to get? What's the difference of potential right there?
4 volts.
So we have 4 volts difference. So we're going to read 4 volts. So the bridge is unbalanced. So that answers the question. Do they all have to be the same? Yes, it does. All right. An ohm meter uses this arrangement similar to this. So an ohm meter uses an arrangement similar. Let me see. So this is, what does that mean?
Potentiometer.
Okay, a variable. And this here can be, they call it R of X. Call this one R1 and this one R2. And of course it's going to have the voltmeter here like that. And this says, I'll let you get that kind of drawn out. This is R3. Of course this has to finish off like that. And, yes.
I'm a little bit confused because if it's a series parallel, right, at the beginning it is parallel, wouldn't the voltage be equal across the parallel circuit?
Total,
The total should be
the
equal?
total's the same.
Okay.
Each side had 12,
Okay.
but it was
that's what I was
4 and 4, 8 and 8 were in balance. But if it's 4
and 8
and 4 and 8 and 8, we're out of balance in the middle.
in the middle. Okay. That's what I was confused about.
All right, got that? All right, so you're going to need to look at your drawing because I'm rolling down R1, 2, and 3 are precision variable resistors. And I believe the variable is like internal to the meter.
You believe the variable's what?
Internal. Like you don't have 4 knobs to change these.
Isn't it like, so like for the case of the Citizen meters, whenever we change that main dial, it selects those different resistors to be changed?
I believe you're changing this one here, R3.
Okay.
So Rx is the item to be measured. R3 is the variable zero out resistor. So you have to calibrate them sometimes. You got to get inside and change the other ones and make sure it's all balanced out. So if it's not balanced, that's where you go.
Do resistors change their values after a while? Is that what you're saying?
We're out.
They wear out?
Something? I don't know.
I mean, I don't know like that.
I'm guessing.
The heat.
I'm not an engineer. And then it says a galvanometer, Galvanometer, G, is inserted in the circuit to indicate the condition of balance. So where do you think that's going to go? I think that's going to go where I had the V right there. And SERT is inserted to indicate the condition of balance. So if we go back up and look at the drawing, and let's think about it a little bit. I kind of want to. All right, so this is the black lead. This is like the red lead on the ohm meter. Looking at ohm meter now. Because Rx is the what?
It's the value to be measured.
The thing we're measuring. So we want to measure this thing, so what do we do with the red and the black?
Connect them.
Touch them together. And then we adjust R3 until R1, R2, R3, and the thing we want to measure are in balance. And the voltmeter then reads 0. Then we take it off, and what happens to the needle? Goes back to infinite. And then we put it across a resistor we want to measure, and that creates an out of balance circuit that's been calibrated. A voltage will then go through the little voltmeter, indicating the difference. And it's calibrated to show resistance. So we had our Rx right here is what we're measuring, but I kind of, oops, this probably will screw everything up. Yes, it sure did. Can I do Control Z and put that back? I can. All right, so just pretend like Rx isn't right there. And so we want to measure, right? That's what we're doing. This is, I just moved Rx out here. That's what we're measuring. It's an ohm meter. Everybody got it? But you decided that you're going to be a little bit different, and you are going to measure it with the power on. So what does that do to the thing?
Squiggling would do.
Yeah, that wasn't designed to do that, was it? No. Where is this battery right here? It's inside the meter. So again, this is an ohm meter. So we don't put a battery here. We put the leads together.
Will it read 0?
We adjust R3 until we have a Wheatstone bridge in balance. So at that point, what would R2 have to be as far as resistance goes? What is R2 to keep?
So
Uh,
0, if we're zeroing out R3.
Some of you are awake. What is this again? What kind of meter? Ohm meter.
It's got to equal the resistance of all the wires of the two wires.
He's actually right. So I want to zero out the meter, right? Remember, you guys? Zero out the meter. We take the red and the black, we put them together, and we adjust the little knob. When I adjust the knob, what am I adjusting?
R3.
R3. Okay? So now it reads 0, which means there's no difference of potential. And so this is the little meter movement right there, because it's a voltmeter or a galvanometer, right? That's just what it is. Right there in the middle. There's our meter. What's it doing? It's a little tiny voltmeter that's telling us resistance, but it's really just a voltmeter,
Which is actually just an ammeter.
which is just an ammeter.
Which is just an ohm meter.
All right. So, all right. So please don't put it on ohms and see how many amps come out. All right. Right. Okay. So we zero it out. So when it's zeroed out, these are touching. There's no resistor there, and it's touching. And we zero this out. How many ohms do you think this is right here? These wires and stuff. And you should know because you did this with a digital meter, and you got about what? 0.5, 1, 3. Some of you got like 38. Some of you got 112 because meters. All right. Well, let's just say it's like, this is about an ohm's worth of wire here. Then what is R2 going to end up being? About an ohm. I mean, I don't know how internally that actually works, but that would have to be that. And so it's balanced out here so that.
R1 is like a control, kind of like a reference.
Yeah. I don't know all about this. When it comes to ohm meters, I think it's got to be a little more
But you
complicated
gotta have
than
some
that.
type of standard.
Yeah. So, anyway, but trying to kind of help you vision that. So that is a Wheatstone bridge. So the big takeaway from a Wheatstone bridge is oftentimes what you will do is you will have it set up, and what they're trying to do is they're trying to figure out if there's a difference of anything from here to here, and if there's a difference between here and here, I need a signal. That's how you do it. You can balance it out, and then if anything changes over here, You can do all kinds of stuff with this if you think about it. I need a light to come on if, I don't know, this gets hot over here. And so I can have a Wheatstone bridge that's completely balanced out. And if one of these things gets hot, it changes the resistance. And if it changes the resistance, what happens to the voltage current flow? Falls out of balance. So I get a signal which could light up a light or ring a bell or something like that. So that's how you would do it, something like that. Yeah.
I know you referenced that like later in the course. I forget the name of the professor, but he was talking. You were talking.
Oh, Phil.
Phil.
Yeah.
He does a lot of like fire detection systems.
Yeah.
Because I know at least at my job when we're loading the pit, just above us is those fire detection systems.
Yeah.
So those aren't just smoke detectors. Those are actually.
Oh, they could be smoke detectors. There's different types of systems in aircraft.
Yeah.
Not just smoke, but rate of rise, heat, all kinds of
I was
different
gonna
things.
say, because you could talk about like the temperature could change the resistor, so it's all balanced out, and then temperature in some part can change the resistor. And
Yeah, I don't know this. I mean, there's so much I don't know. I could write a book of all the stuff I don't know. But somebody's like listening, going, "No, you idiot." We could do something like with the smoke detector. It does have like some of them have a photo cell. Some of them have little bits of radioactive material. But I'm just thinking here. What if we had to make something like this and want to make a smoke detector? Well, we could put something right in here. The variable, we could make it in balance, and the variable has some sort of photo detector that, as long as it has a clear beam between two spots with this photo detector, like a little light and a receptor, that it balances out. But if anything got between the light and the receptor, it would change the value of that, which would make it out of balance, which would cause a voltage to go across here, which would then go to a signal that would get amplified and make the thing go off.
So it kind of make it like it would be a relay that causes that to go off.
Well, yeah, at that point, we'd probably be using transistors and stuff to make the amplifier that worked. But as you can see, you could do all kinds of stuff with that, just by getting a little out of balance. So that's a Wheatstone bridge, which I think is very important to understand, and I hope that you kind of got it through my
Hey, Kevin?
crazy. Yeah.
So I'm trying to picture how you're zeroing out the RX part of it.
Well, maybe don't,
So am I connecting?
because I'm trying to too. So I don't know if that's an entire.
So my leads go on the resistor, and then I'm zeroing out that resistor.
Yeah, right here. You're turning R3. You're adjusting R3 until R1 and 3 are completely imbalanced, and 2 and RX are completely imbalanced. And then there's no voltage across here, so it's going to read 0.
So it'd be like if I'm zeroing out my leads normally when I read lows, but instead I have my leads connected to the resistor and I'm zeroing out.
Well, you wouldn't do that, because we never do that, right?
Right, that's what I'm.
No. When we connect the two leads,
Right.
we adjust R3 until it's all in balance and there's nothing across here, and the meter will read
Zero.
0. Then we take it off, and what's that meter do? It was on 0. What does it do?
Goes to infinity.
Slams all the way over the other side of the meter, right? It goes to infinity because we disconnected this, and then things are different.
It's all interior. Like that's all.
It's probably not that simple, but if you can understand that concept, because to me, there's a lot about this I don't understand with the ohm meter. I just don't get into them like that. It's like, well, I don't want to confuse you, but why is R2 set to measure this? Is it set to that value? And then anyway.
It'd be amazing if we open one of those up there for 3 of those.
These are questions that I start to come up with as I start doing this. I should look into that. So this is kind of a first run on this particular concept. Let's see. If the meter is balanced out, the meter will show an indication proportionally out of balance. Okay. Yeah. The meter is out of balance. Then it shows voltage, which is an indication of the amount of out of balance. Of course, there's a lot more going on in here, because if you think about the ohm meter, you've got the R times 1, the R times 1,000, R times 10,000, which changes these resistors down in here to get the scale difference. So again, there's more going on. But if you understand at least the simple concept of a Wheatstone bridge, that if this is 20 and this is where to go, that's out of balance. If looking for the balance. There we go. This one's balanced. If this is 10 and this is 10 and that's 20 and that's 20, then there's no current flow. And the meter reads 0, or we get the indication we get is 0, whatever system it's in. Because this would be in more than just ohm meters. Trust me, it's in everything. But if we get an out of balance, then we get a voltage difference, which will have a meter, which will indicate something or do something. I mean, you could do anything with this. You could make this into an oil pressure gauge. So when the engine is off, our 1, 2, 3, and 4 are in balance. They could turn on the switch to the aircraft to give some power across this. You have no oil pressure, and it would be completely in balance. And so what would the gauge read? 0. And then as I start up the engine, I could have an oil pressure transducer up on the engine, which the more pressure it gives, the higher the resistance. And so as it got more resistance, what would happen to the balance? It would go out of balance. So what would happen to this little voltmeter would start to read voltage, right? And let's just say the more oil pressure I had, the more and more and more voltage it started to read. Well, what would my gauge show? It wouldn't say volts. It would say oil pressure. So that would be an electric oil pressure gauge right there.
Could it do temperature as well?
Absolutely. Just change one of those to a temperature sensing resistor.
You could do literally anything.
Literally, not literally. Figuratively anything. That went well. And that probably should be, hang on. Just going to make a note to self. I think that came a little earlier than it should have. 7, 8, Wheatstone Bridge. After. There we go. Do that later. All right, 7, 8, 9. All right, we're kind of going back a little bit now towards meters. And this is more about meters, not about you personally. Sensitivity. Sensitivity. Defined as the amount of current flow needed to create a full scale deflection. Sensitivity, the amount of current needed to create a full scale deflection. If we went to here, went back until we got to right there, and oh, come on, it doesn't say it on here. It's down there. We can't really see it too well. I thought some of the meters actually said it. My bad. All right. Oh, well, it's in my notes here. So a Simpson has a DC voltage sensitivity of 20,000 ohms per volt. In other words, 20,000 ohms at 1 volt equals, it's going to blow your mind, E equals I over R. So E, 20,000, let me see, 20,000, 1 divided by 20,000, there we go, equals 1, 2, 3, 4, 5 A. So 1, 2, 3, 4, 5, 6 50 microamps. That is to say that if I was measuring 1 volt, how many amps is it going to steal out of my circuit? 50 microamps. So for every volt that I'm reading, it's stealing that much out of my circuit. Which is not very much, is it? No. So that's a good meter. All right, let me see. Say, what if I was measuring the 2.5 volts? I have it on 2. I kind of just tend to default to, let's just say, the maximum. So it's on the 2.5 volt setting. How many ohms is it going to steal?
How many ohms?
Yeah, that's not what I meant to say at all. How many amps?
1.25 milliamps.
125 microamps.
Let me see. I don't think I changed this here. So how many ohms would it take? So it would be 20,000 times 2.5 equals 50,000 ohms, and that would be equal how many amps? One, two, three, four. Did we do the first one wrong? Because why am I getting the same answer?
Would be
2.5 times point.
Yeah, why is it giving me the same answer? Let's check the answer for number 1.
20,000 ohms per volt would be
1, 2, 3, 4, 5. So that's right. I got the same answer. And then let me see. 2.5 divided by 50. Same answer. Let me see here.
and wouldn't it be 0.00012?
Oh, there we go. Well, I don't know here. I got E is 2.5. The R is 50K. Same thing.
So Ohm's law is lying.
Just Ohm's law. So 2.5 volts. Oops. At 500K ohms, right? Equals 0.00005,
50K.
which is the same as 50 microamps. Because it's 20,000 ohms for every volt. How many volts do we have? All right.
It'd be 50K, not 500K.
Yeah.
Oh, sorry, 50K. 50K. Well, all right, taking it one step further, what if we're on the 10 volt setting?
Oh, you're saying that.
200,000 ohms.
200,000 ohms, which equals how many?
50 milliamps.
0.0005, which is 50
Microamps.
microamps. So it just takes the same. Full scale deflection takes the same amount. Well, that sounds kind of
Got
weird,
one less
doesn't it?
zero.
But wait a minute.
Current stays the same in series.
Let's think about the inside of the meter. Why does it stay the same? Because a full scale deflection is a full scale deflection because that's how much current it takes to make a full scale deflection. So if we go back to what does the sensitivity mean?
Full scale deflection.
Define the amount of current needed to
Create a full scale deflection.
create a full scale deflection. So if I have it on a 2.5 volt, how many volts does it take to make a full scale deflection? 2.5. And it takes how many amps to create a full scale deflection?
50 microamps.
That's the same across the board for a Simpson meter. That's how many amps it takes to make the two electromagnets go full scale deflection. I should do it this way for you because I think it's that way for you. So there we go. I wrote a note. Note that it is not the actual voltage of the circuit measured, but by the full scale deflection. All right, let's just end it there because we'll have fun tomorrow. I will.